Hello guys, so welcome back to our third part of lecture 3, in which we're gonna discuss another type of current that happens in semiconductors, which is called diffusion current. So we have some diffusion here. So let's link it to another phenomenon that we all know, okay, in which ink in a water like this. This is an ink in water. So basically, if you drop, one drop of ink into a cup of water like this, it will diffuse all over, the cup in the water. So basically, we have some, similar phenomena in our semiconductor. So when we inject somehow, when we inject, some carriers in one side of a sample, silicon, for example, or any type of semiconductor, then at that location of the diffusion or the injection, we will have higher density of this carrier rather than or bigger than the density of that carrier in the semiconductor. At that time, when we have different or non-uniform distribution of the carriers, there will be a current, there will be a movement for these carriers from the high concentration regions into the low concentration regions. So something like this. So here we have, semiconductor material in a sample of semiconductor material. Then we inject here, some carriers from one of the sides, this side. This will create non-uniform distribution of this carrier. So this non-uniform distribution will make the carriers to go in the direction of low concentration, from the high concentration region to the low concentration regions. Okay, and that's basically a current. So we are here talking about holes or electrons, and when these electrons or holes moves, this will create a current, and this current comes from the phenomena of diffusion. Okay, so let's take, for example, an n-type sample like this. This is an n-type sample. Okay, let's change the color here. Okay, then we inject some electrons from one of these sides. Okay, this will create a profile, a concentration profile that is not uniform. So in all what we have discussed so far, when we say we doped with holes or electrons, that means, or we assume, implicitly, that the density of electrons or holes is uniform. If you take any volume of the material, and measure the density of holes or electrons, they will be the same. Okay, but here, because of the diffusion at one side, not at the other side, then this will create some discrepancy or non-uniform distribution of the carriers. Okay, this distribution can take any shape, but it can be linear. I mean, it can be non-linear, but in all cases, the side of the injection will have higher density than the other side. So, for example, it may be something like this. Okay, it may be linear, it may be non-linear. Here, for example, it's a general case non-linear. Okay, so this is n, the density of n now. So the density, if this is, for example, the x-axis, the density of n here, n of x, let's call it nx0, the beginning of axis x, which is 0. And here is, for example, L. This is the density at L. Of course, nx of 0 is larger than or greater than nx at L. Or n of 0 is larger than n of L, because x is equal to L and x is equal to 0 at the beginning. Okay? And this is called now n of x, because n now is dependent on x. Previously, I said that we always assumed uniform distribution. So n is independent of x. I mean, at any x, if you measure the density of the electrons, for example, it will be the same. At n x equal to 0, n equal to 1, n equal to L, everywhere it's the same. But here, no. Now, because of that non-uniform distribution, electrons will move from the high concentration region to the low concentration region toward the x-axis in that case. Okay, and when the electron moves, this will create a current. So there will be a current, and this current In, as usual, the current is in the direction of the positive charges, or opposite to the direction of the negative charge. So the negative charge is moving toward L, so In will be in the opposite direction. Okay. Okay, so let's now, calculate this current. So this current is basically, so In, let's go back to our fancy, color, blue. In is proportional to, the distribution. If you have more non-uniform distribution, okay, more exchange, in N, then you will have more current. I mean, if you have higher concentration at regions than other regions, this will create more current. If the difference between these two regions in concentration becomes larger, the current will be larger. Okay, so how to express this mathematically? This is basically the slope of N versus X. So I is proportional to dN of X by dx. How to understand this, in a more easy way. So let's assume, for example, a linear relation like this. Two linear relations in N of X. Let's call it N1 of X, so this is X. And here is, for example, one slope. So this is dN1 of X by dx, which is the slope of that line. Now let's take another line, another relation now. So this is N2 of X, and both are drawn against the same axis X. So this red line now has another slope, dN2 of X by dx. In that case here, dN2 of X by dx is greater than dN1 of X by dx. So we expect to have more current with dN2, or I'm sorry, with N2 of X than the case, or the current in the case of N1 of X. Okay, so In is proportional to dN of X by dx. Okay. What else? So again, let's go back to the definition of a current. A current is, the amount of charge that passes through some cross section in some time. So you just, divide the amount of charge by the time. This will give you the current. So if we have more charge, we will have more current. So if we increase the cross-section area, okay, if we increase the cross-section area of the sample, this will increase the current as well, because now more, more charge will pass through the same, more charge will pass through at the same time through the cross-section area. So I is also proportional to the area. Okay, so basically In, because we are talking about any sample now, is equal to something, some constant multiplied by A multiplied by dN of X by dx. We are talking about the amount of charge, so we must include Q, the charge of an electron, which is 1.6 10 to the power minus 19. And we have here a constant for this proportionality, which is called dN in that case, because this is, in a type material. And this dN is called So this is a constant for the material. And this is basically it's corresponding to mu n in the drift current. So we have mu n in the drift current. It was also a constant for some proportionality between v, the drift velocity, and E. Here we have dn. And they call it diffusivity. Diffusivity. Or diffusion constant. Okay, diffusion constant. And again, for silicon, we have dn. For other material, we have dn, but with other value. Okay. Again, we don't like, to relate to the geometry. Okay. So we're gonna divide by the cross section area and get the current density. So Gn, just like what we did with the drift current. So Gn is just equal to In divided by A, the cross section area. So this will be Q dn of x by dx. One might say here that E or the electrons are moving in the direction of x, like the example here, and I is opposite to z. So there should be some negative number, some negative value here. I mean, so some negative sign. And the answer is that dn by dx itself is a negative. I mean, when you calculate it, this will result in a negative sign. Okay, basically because if we look at the n of x here, n of x is decreasing with x, and if you have a function that is decreasing with x, then its derivative with respect to x would be negative. Okay, so the n of x here is negative because n of x is decreasing with respect to x. Okay, good. So this is In and this is Gn. Now let's do the same for holes. If we have now a p-type material, so this is number 1. Now for number 2, which is p-type material. Can we do the same? Yes. Assume that we inject some holes at some side of the sample, just like this. This is holes. How we do that? That's not our problem now. Okay, we're gonna touch on that, when we take the transistors. If we inject the holes at some side of the sample, then again we will have some, change or some non-uniform distribution of holes across the sample. So we might have something like this. It might be linear, it might be non-linear, So this is general case, it's non-linear. Okay, and here is b of x now. Okay, and again b at 0, and if here, for example, L, b of 0 is greater than b of L. If this is the x-axis. So once there is an area with higher density of holes than another area, then holes will move from the high density area to the low density area, and that would create a current, and this current now is in the direction of holes. It's not opposite, it's in the direction of holes. Okay, and we have IB, and IB will be very similar to what we see, but with another sign. So here it will be minus Q and dB, not dN. Again, like what we have for the drift current mu n and mu b, we have here dB and dN. A dB of x by dx. And before we continue, okay, I want you to think about why we have different sign here, because this is now negative, okay? So give yourself, 1 minute just to hold the video, pause the video, and give yourself 1 minute and think about it, okay? Okay, let's go back, assuming that you think about it and get the answer. So the answer is dB by dx again is negative. So dB by dx is negative because again b is decreasing with x. Okay, so negative will cancel this negative. So this negative will cancel out the negative sign in the equation. Okay, so it will be positive at the end. Okay, and again we have GB as well. It's equal to minus Q dB of x by dx. Okay, now the general case, number 3, the general case. Like what we have taken with the drift current, the overall diffusion current is the addition of, or the summation of the IN and I drift from the carriers, negative electrons, and IB from positive electrons. So we have here the same stuff as well. So J total, J diffusion total is equal to Gn plus Gb. Gn plus Gb. So let's add them together. So this will be, we can take the Q as a common factor. So we have here dn of x by dx minus dB of x by dx. But you will notice here, let's go back and, this is J total. If we analyze this relation and check the final, the sign of each term, you will find that this term here is negative. And this term here will be positive at the end. So let's do it. So Gn is negative, Gb is positive. They are so with the drift current, if you remember, J total was positive. J total was positive. I mean, or we can say in another word that IN drift and IB drift both were positive. Here they are opposite in sign. GB is positive and Jn is negative. Okay, and why is this? So the answer here lies, if we look carefully into these two, samples. Look, IN is going in the opposite x of x direction, and IB is going in the direction of x direction. So they are opposite. So basically, if we have the general case, I mean you have electrons and holes injected at the same time. Okay, you have, for example, a hole concentration like this. This will make holes to move in that way, and IB will be in that way as well. And then you will have, maybe larger or smaller, you don't know, but generally you have something like this, but it might be larger, or it might be like this. Okay, so the electrons will move in that direction. So IN will be in the opposite direction. So IN and IB, let's state this here, IN and IB are in opposite directions. That's why one of them is negative and the other is positive. It's not like the drift current. No. There, if you study, if you go back and study this lecture again, you will find that both currents were in the same directions. But here now, they are opposite. Okay, that's why at the end we subtract something from another. Maybe Gn is bigger, maybe Gb is bigger, So we'll subtract. So the overall is less. Okay, so let's take an example. We have here an n-type material, and we inject electrons here at one of the sites. Okay, such that the relation between, or the distribution of n, the density, is like this. It's linear. So it's a linear relation between n and x. Okay, and that's make the analysis easy, because you can dn by dx at that time will be the slope, and the slope for linear relations are very easy to to calculate. Okay, so find Gn. This is the question. Find Gn and sketch it. From 0 to L. This is 0 and this is L. Okay. Okay, we know that Gn equal to, this is the solution. Gn is equal to Q dn dn of x by dx. We need to know dn of x by dx. And the dn, of course. Okay. So dn of x by dx, we should first get the relation, then we find the slope. So n of x as a function, basically it's a linear function. So it's ax plus b. So this is the slope. This is the constant intersected with the y-axis. Okay, so the slope here is very simple to calculate. We can take 2 points, and so here point 1 and point 2. So this point has the axis. The x is 0, y is, I forgot to mention this, so y here is n. So n is the density of the electrons at at x equal to 0, n capital. It's a constant. Okay. And here's the density. Here, I'm sorry, Lx, the x-axis is L, and the density is 0. So the slope is y minus y over x minus x, y2 minus y1 over x2 minus x1. y2 is 0, y1 is n capital, and n capital is part of the question. I just forgot to mention it in the first place. So you once it gives you instead of a number, it gives you some symbol, so you can consider this as a constant. You don't care about its value, but you can assume it's known. Over x2, which is L, minus x1, which is 0, so this will give us minus n over L. This is the slope. And b, which is the constant, the intersection of the line with the y-axis, n capital. So n of x is equal to minus n over L x plus n. And you can check over yourself if this relation is correct or not. Basically, you substitute with one of these 2 points, with x, and you should get y, same y. So here, for example, x is equal to 0. If we put x equal to 0 in the relation, this term will go away. So this will give us n of x equal to n, which is correct. if we substitute with that one, if we put x equal to L, L will go with L. So we'll have at the end n of x equal to minus L plus L, which is 0. And that's correct. Okay, good. If this is silicon, so let's assume it's a silicon here. For silicon, dn and db are known as well. Okay, so for silicon, so this is the first part of the solution. Second part, for silicon, we know dn and db. So dn is equal to, let me get it for you, 34 centimeter square per second, and db, of course, we will not use dB in this example, but just to know it, is 12 centimeter square per second. Okay. So at the end, Gn is equal to Q, and Dn is, write it Dn. We know its value, but at the end, since not everything is known as a constant, as a number, then just write it as a symbol, dn, and dn of x by dx is just equal to the slope, which is a here, which is minus L minus n over L. And here is what I told you, that dn of x by dx will be negative. So don't worry about the sign. dn by dx will be negative, and here is an example for it. So at the end, Gn equal to minus Q dn n over L. It's a constant. So Gn here equal to constant. So when we sketch it, and this constant is minus. So let's sketch it with x. This is, the axis x. Here is Gn of x. It's just a sketch. So just to choose any point under the x-axis to make it negative, and just to draw a line, straight line, constant line from 0 to L. And what is the value here? The value is minus Q dn n over L. Okay? So this is basically a very good example to apply or to illustrate more, the diffusion phenomenon and the diffusion current. One last observation here is that, again, dn is greater than db. This is 34, this is 12. This is almost 3 times bigger. Just like the case of mu n and mu b. Again, that means that electrons can diffuse more than holes. Okay? Electrons can diffuse easily than holes. That's what makes dn, its diffusivity, its tendency to diffuse, much larger than the diffusivity of dB. Okay, one last thing before we finish this lecture is what's called Einstein relation. It's Einstein, our Einstein, So Einstein has also some interest in solid state materials, okay, and the quantum mechanics. And this is one of his, actually, very intelligent ideas and discoveries, in which he connects the drift phenomena to the diffusion phenomena. So basically, the diffusion and the drift are two, separate phenomena. Here is the current, is generated using, electric field. In drift is a drift phenomena, and in the diffusion phenomena, the current is generated using the change or the non-uniform distribution of the density of the carriers. Okay, but he could relate them to each other, and he found this interesting relation that d over mu. So this is the diffusivity of the material, I'm sorry. Yeah, it's a constant for the material, but it's it's a different number for the holes and electrons. And here is the mobility. This is for the diffusion phenomena. This is from the mobility phenomena, and he discovered this is equal to constant at the same temperature. And he found that this constant is actually kT over Q. K is Boltzmann constant, T temperature in Kelvin, over Q is electron charge. So this is electron charge, 1.6 10 to the power of minus 19. This is Boltzmann constant. This is temperature in Kelvin. Okay, and not just that, he discovered that d over mu, if you look further here, d over mu is not just a constant, it's actually some sort of energy, because kT, as we said, if you have a temperature, this temperature is just an energy, and this the amount of energy is multiplying the temperature in Kelvin by Boltzmann constant. Okay, so kT is a thermal energy at temperature T. And energy is measured in joules, right? But if you divide it by Q, the electron charge, it will be electron volt. So this is just an energy in electron volt. So this term here is energy in electron volt, because kT is in joules. When you divide it by Q, you convert it from joule to electron volt. So it's energy at the end. Okay, guys. So that's it for the currents inside the semiconductor. Now we are ready now to express or to illustrate or to introduce to you the first device that we're gonna use in our circuits, which is a diode. Okay, so all this introduction, all these 3 lectures, just to understand the basics, the foundation, and that we need to to have this our first device in semiconductor circuits, which is the diode or the PN junction. Okay, and this will be our topic in the next lecture. So see you. Bye bye.